Good evening, traveler, and welcome back to a place where science and story become one. You already know the universe is vast, mysterious, and far beyond what the eye can see. Tonight, I'll guide you through that mystery, step by step, so that even as you drift toward rest, your mind awakens to truths as real as the stars themselves. Thousands of listeners have joined this journey before you, returning night after night, because here, you don't just hear a story, you enter it. Every tale is told in an immersive style, placing you inside the adventure, so you don't simply learn about the cosmos, you live it. But let me ask you something. What truly happens when a star dies so completely that even light cannot escape? Where does matter go when it passes the point of no return? And if everything that falls into a black hole is lost, what does that say about the information written into the fabric of reality? These are not simple questions, and tonight we'll walk through them together. If you've ever wondered what lies beneath the surface of stars, or how the smallest quantum events ripple into the largest structures of space-time, this is where you belong. And I want your voice to help shape where we go next. In the comments below, share which mysteries of nature or the cosmos you'd like to see unraveled in this immersive style. Every suggestion builds this channel into something larger, a community of travelers who journey together through knowledge and wonder. No other channel takes you this deep, this calmly, and this directly into the story of the universe. This is where imagination and science meet, where fact becomes experience, and where your curiosity guides the road ahead. So settle in, breathe deeply. Let the forest, the stars, and the flame of truth carry you into tonight's journey. The story begins. You pause beneath a tree and place your hand against the bark. At first, it feels ordinary, cool and rough under your palm. But inside the leaf above you, something extraordinary is happening. Something so efficient and precise that human scientists still cannot fully replicate it. The tree is performing photosynthesis, the process that powers almost all life on Earth. When sunlight strikes the surface of the leaf, it arrives in packets of energy called photons. These photons are absorbed by molecules of chlorophyll, the pigment that gives the leaf its green color. The absorbed energy has a simple goal: to move to a reaction center inside the leaf, where it can be converted into chemical fuel. But here is the remarkable part. Inside the leaf, this journey does not follow the ordinary rules you would expect. Instead of traveling in one straight line and losing energy along the way, the photon's energy behaves according to quantum mechanics. In the quantum realm, particles can exist in multiple states or take multiple paths at the same time. Inside the leaf, the absorbed energy doesn't just move randomly from molecule to molecule. It explores every possible path simultaneously, like ripples spreading across a pond. This phenomenon is called quantum coherence. Once all the possible paths have been explored in parallel, the energy collapses into the single most efficient route, ensuring it reaches the reaction center with almost no loss. For you, standing here in the quiet forest, it may look simple: sunlight falling on leaves, a tree drinking light. But within each leaf is a process billions of years old, one that works with a precision beyond any human technology. No solar panel designed by engineers achieves such near-perfect efficiency at moving energy. Trees do it automatically, silently, every second the sun shines. As the reaction center receives the energy, it converts it into chemical bonds, splitting water molecules into hydrogen and oxygen. The oxygen escapes into the air. You breathe it in with every calm breath you take beneath this canopy. The hydrogen helps create sugars, fuel for the tree itself, and, eventually, for all the creatures that eat its fruit, its leaves, or even the animals that eat those creatures. The tree is not just standing here passively. It is an engine, powered by sunlight, using quantum mechanics to feed the entire chain of life around you. You withdraw your hand, but the knowledge lingers. The simple act of touching a tree has placed you in contact with one of the most elegant quantum systems on Earth. The air in your lungs, the soil beneath your boots, the bird calling in the distance. None of these would exist as they do without the invisible dance of photons inside these leaves. You follow the path deeper into the forest, the quiet stream curving at your side. The water glimmers faintly under the moon, but you stop not just to admire its beauty. Tonight, you want to understand it. You crouch at the bank, scooping a handful of water into your palm. It slips easily between your fingers, pooling back into the current. At first glance, water seems simple, almost too ordinary to think about. But water is one of the strangest substances in existence, and life as you know it would be impossible without its peculiar, almost paradoxical qualities. Each droplet you touch is built from countless molecules of H2O. That means 2 hydrogen atoms bound to 1 oxygen atom. The bond is not a perfect balance. Oxygen is greedy for electrons, pulling them closer and leaving the hydrogen side slightly positive while the oxygen side becomes slightly negative. This makes water a polar molecule, like a tiny magnet. When billions of these polar molecules cluster together, they align and tug on each other, forming hydrogen bonds that give water its unique personality. Most substances get denser as they freeze, but not water. When it solidifies into ice, the hydrogen bonds lock into a crystal lattice but holds the molecules apart, making ice less dense than liquid water. That is why ice floats. Without this property, oceans and lakes would freeze solid from the bottom up, trapping life beneath miles of ice. Instead, ice forms a floating blanket that insulates the water below, allowing ecosystems to survive, even in the coldest winters. You watch the current tumble across rocks and realize that even this flow is shaped by the laws of physics. The second law of thermodynamics says energy always moves toward disorder. That might sound grim, but it is this principle that allows water to carve valleys, feed rivers, and power cycles of life. The stream is constantly moving from high energy to low, from mountain to sea, carrying with it dissolved minerals and nutrients that nourish entire landscapes. The patterns of turbulence, those curling swirls and eddies, may look random, but hidden inside them are fractals, structures that repeat at different scales, from tiny ripples at your feet to massive storm systems that circle Cree. The globe. These patterns are how nature moves energy efficiently, distributing it across scales in ways engineers still study to learn from. You dip your fingers back into the stream and consider its role as a solvent. Water dissolves more substances than any other liquid known, earning it the title of the universal solvent. The reason lies in its polarity. Positive charges on one side, negative on the other. Water molecules surround and pull apart compounds like salts, sugars, and proteins. Without this, the chemistry of life could not unfold. Nutrients could not travel in blood. Cells could not exchange information. Energy could not flow. Even here, in this quiet stream, water carries traces of stone, soil, and sky, dissolving, transporting, and recombining them into endless forms. Life drinks, breathes, and builds itself upon this quiet chemistry, moment by moment, molecule by molecule. Though water's chemistry explains much, scientists suspect there is even more hidden. Some research suggests water molecules can form fleeting quantum networks, aligning in patterns that last only trillionths of a second, but influence how proteins fold, how DNA stabilizes, and how, quote, energy moves in living systems. These patterns are invisible to your eyes, but they hum constantly beneath the surface, as fundamental to your existence as your heartbeat. You rise from the stream, wiping your hand against your cloak. What seems like a trickle of water flowing through a forest is in fact a vast stage for the laws of physics and chemistry. Its hydrogen bombs hold ice above liquid, saving life from endless winters. Its solvent power dissolves nutrients, carrying them into every living thing. Its currents embody thermodynamics in action, energy cascading toward balance. Even here, in silence, water whispers of the deep principles shaping the world. As you step away, you realize you are not merely walking past a stream. You are walking beside one of the oldest and most powerful forces of nature, a companion to life from its very beginning. You leave the stream behind and follow a narrow path through the dim forest, the canopy thinning until a slice of sky opens above you. The night is clear. You hear the wing beats before you see them, a faint rush like fabric brushed by air. Then shapes pass across the stars in wide arcs. Migrating birds cross the valley, unspooling a line that stretches farther than any road. You tilt your head and feel the quiet pull of curiosity sharpen. You want more than wonder. You want to know how a creature the size of your hand can cross continents and return to the same grove year after year without losing its way. You stand very still and imagine stepping into the eye of a robin, a warbler, a thrush. Not as a metaphor, but as a mental microscope. Inside the retina is a protein called cryptochrome. Its job is tied to light and timing, but part of it may serve as a compass. The core of cryptochrome holds a molecule called FAD, flavin adenine dinucleotide. When blue or green light strikes FAD, an electron is promoted, then passed to a nearby amino acid chain, creating two partners with unpaired electrons. These two partners are a radical pair. Each electron carries a quantum property called spin. Spins can be aligned or opposed, and those configurations have names. When two spins point in opposite directions, the pair is in a singlet state. When they point the same way, the pair is in one of three triplet states. That difference is not just a label. It changes how the pair reacts chemically. The Earth's magnetic field is weak by everyday standards, but at the molecular scale, it is significant. Magnetic fields interact with the spins of unpaired electrons. In cryptochrome, the local magnetic environment slightly shifts the rates at which singlet and triplet states convert into each other. The electrons also feel local magnetic influences from nearby atoms, called hyperfine interactions. Because those local fields are oriented differently with respect to the protein, the outcome of singlet to triplet interconversion depends on the angle between the cryptochrome molecule and the Earth's magnetic field. Put simply, the same radical pair will have different reaction yields when the bird's head is pitched or tilted differently relative to the field lines. That difference in yield matters because the chemical products of the singlet root and the triplet root are not the same. The retina is a sheet of light-sensitive chemistry, and small differences across millions of molecules average into a faint visual pattern. The current view among many researchers is that the bird does not see a compass needle. It sees a dim overlay on its normal vision, an intensity pattern aligned with the magnetic field. The effect is inclination only, not polarity, which means the bird senses the tilt of the field lines rather than a simple north or south arrow. That is why many birds learn to orient by the angle of the field rather than its absolute direction. They can tell poleward versus equatorward by the steepness of the inclination that folds across their view. Now, you shift your attention to timing. Radical pairs are fragile. The two electrons can maintain coherent spin relationships for only a short time. Thermal noise, random collisions, and internal molecular vibrations jostle the spins, washing out the correlation. Yet even a brief coherence, lasting fractions of a microsecond, is enough for chemistry to diverge in a measurable way. In the eye, light constantly refreshes cryptochrome, repeatedly creating new radical pairs. The system does not need perfect coherence for long. It needs it just long enough for the reaction yields to carry the signature of direction. You step back mentally to the whole bird, gliding between stars. A compass that depends on light would fail in darkness, which fits what many studies report. Birds tested in dim blue light show magnetic orientation. Birds in red light often do not. The protein effect relies on the energy of shorter wavelengths to kick the electron into motion. When researchers apply weak, oscillating magnetic fields at specific frequencies, birds that were oriented can become disoriented. The oscillating field perturbs the delicate singlets to triplet mixing, like tapping a tuning fork until the note wobbles. This disruption is not strong in absolute terms. Even fields far weaker than a refrigerator magnet can interfere if they are tuned to the right frequency range. That sensitivity is a clue. It suggests that quantum spin dynamics are not a side effect. They are the mechanism. You consider an alternative view. Years before the radical pair model was popular, some researchers proposed tiny crystals of magnetite inside beaks or tissues that respond mechanically to the field. Magnetite is a magnetic mineral but can align with field lines and exert forces on ion channels. In some animals, magnetite structures do appear to play a role. In birds, evidence is mixed. Some cells stain like iron-containing sensors, but results vary. And in many orientation experiments, the light dependence and radio frequency disruption point more cleanly to the radical pair pathway in the eye. It is likely that more than one system contributes to navigation. A robust traveler uses every cue available. Sun position, star maps, odors carried on wind, landmarks, low-frequency sound, and the magnetic field can combine into a layered guidance system that persists even when one channel is noisy. You look back up at the flock. A robin is not solving equations. It is running a biochemical program that evolution minted from trial and error. The retina presents a faint pattern, stronger when the bird's head is aligned at the correct angle. Neural circuits, trained by experience, translate pattern into behavior. Turn this way, and the overlay brightens. Turn that way, and it dims. Over many nights and many birds, such rules are enough to trace lines across continents. You walk along the ridge as the flock thins and the sky grows deeper. You picture the quantum details again, but more slowly. In cryptochrome, when light excites FAD, the first electron transfer often runs along a chain of tryptophan residues. These act like stepping stones for the charge. The separation creates the radical pair. hyperfine interactions arise because certain nuclei carry their own spins. Nitrogen and hydrogen nuclei in the protein create tiny local magnetic fields that mix singlet and triplet states at rates that depend on orientation. The Earth's field adds a gentle bias. Reaction products feed into downstream biochemistry, changing the availability of signaling molecules or altering the state of the protein. The retina is full of such molecules, arranged in membranes, cross-linked and carefully spaced. The faintest differences can persist when they are repeated across wide areas. You imagine a controlled test. The bird sits in a darkened chamber under light of a selected color. The researchers rotate a set of coils to change the direction of the magnetic field without moving the bird. If the bird uses a magnetic sense tied to cryptochrome, it will turn in response to the changed field only under light that drives the radical pair. If the researchers apply a weak oscillating field at a frequency that matches the difference between singlet and triplet energy levels, the bird's orientation should degrade. Experiments of this kind have been reported across multiple labs and species. The details vary, as living systems often do, but the general pattern recurs. Orientation depends on light. Some radio frequency noise disrupts it. Shielding that noise can restore it. The concept of entanglement appears in many popular accounts. It is safer here to be specific. A radical pair begins as two electrons created at the same moment. Their spins are not independent. In the initial singlet state, the spins are correlated so that if one is up, the other is down. This correlation is a type of quantum coherence that can be entangled. In a warm, wet eye, coherence is short-lived. Yet short-lived is not the same as useless. The chemical pathway reads out the correlation before it fades. That is the key. The system does not need to maintain a delicate quantum state for seconds. It needs it long enough that spin-dependent reaction rates encode directional information. Those rates then become classical signals the nervous system can use. You slow your pace and listen to the wind comb the trees. It helps to place this within a larger picture. A compass tells you only one thing. It cannot alone explain how a bird reaches a specific grove or a specific hedge behind a specific barn. Animals layer sensory maps. During development, young birds learn star patterns. Some calibrate their magnetic compass by sunset glow at the horizon, where the gradient of color sets a reference. Odors define regional signatures. Landforms and coastlines provide course guides that a lifetime of flights refines. The magnetic sense keeps the whole map aligned during cloudy nights or featureless seas. To appreciate the role of quantum chemistry here is not to claim that quantum effects control all of behavior. It is to see that life finds ways to harness subtle physics when a few molecules in the right place can tilt the odds. You think of scale again. The Earth's field is strongest near the poles and weakest near the equator. Its lines dive downward in the north and upward in the south. A compass that senses inclination gives the bird a way to know latitude roughly. When a juvenile departs on its first migration, it can follow an inherited program of directions that depend on the time of year and the light cues it experiences. On later journeys, memory tightens the path. Adults that were displaced during experiments often reorient toward their original destinations rather than simply following their inherited route. A quantum compass sets the axis, then experience and other senses supply the rest. You come to a clearing where the ground warms under starlight. You let your breathing slow and revisit the process in fine detail. This time, imagining the energy diagram. The singlet and triplet states sit at slightly different energies. The local nuclear spins produce hyperfine fields that differ with orientation, so the rate of interconversion changes with head tilt relative to the Earth's field vector. Reaction yields alter the concentration of a signaling state of cryptochrome. That state modulates the sensitivity of photoreceptors or affects downstream proteins in the retina. The result is a patterned modulation, darkest along one axis, faintest along another. The bird learns to treat that modulation like contour lines on a map. It is a visual grammar that overlays the world. You rise and continue walking along the edge of the trees. Your steps are quiet. You consider how fragile such a compass might be. Then you recall that evolution exploits even fragile cues when redundancy exists. If radio noise scrambles the pattern, the bird can wait for quieter skies or switch reliance to odor and wind. If clouds mask stars, the compass stabilizes the course. If landmarks disagree with inclination, the bird may circle, sample both, and choose a vector that splits the difference. The nervous system is a decision-making organ. It weights inputs and outputs a heading. Every night migration is a conversation between senses, each with its own physics. You reach a low hill and sit, watching a faint band of Milky Way brighten as your eyes adapt. You imagine the flock once more, not as silhouettes but as living sensors, each eye full of cryptochrome, each retina resolving a pattern that shifts with every small tilt of the head. Beneath feathers and bone, a quantum process informs a macroscopic journey. That connection is the point. Nature keeps the world coherent by linking levels, from spin to chemistry to neurons to behavior to geography. There is no gap between the forest and the quantum realm. There are only layers that must be read with patience. You let your awareness widen beyond birds, then narrow back with care. A good lesson holds when tested from many sides. You ask yourself, what would falsify the radical pair model? If orientation persisted in total darkness, without any light priming of cryptochrome, that would be a problem. If radio frequency fields at the relevant frequencies never had any effect in careful tests, that would be another. If cryptochrome mutations that remove radical pair formation did not alter magnetic sensitivity, the model would weaken. In many cases, the opposite has been observed. Light wavelengths matter. Disruptive fields matter. Genetic manipulations shift responses. No single result proves a mechanism, but the pattern that emerges across decades increases confidence. You stand again and begin a slow descent toward the valley floor. You pass through a patch of open ground where the air is cooler, then back into trees where the scent of resin deepens. Your mind returns to the basic fact that the Earth's field is present everywhere in this forest, threading every branch and leaf with a vector and an inclination. You cannot feel it with your skin. The bird can, not as a tug, but as a dim map wired into sight. This is not folklore. It is a tested piece of natural engineering, one component within a layered system that grants a small animal the power to cross oceans at night and strike the same branch it left months before. You picture the sunrise that will come hours from now. The light will change color from blue-rich to red-rich as the sun climbs. Cryptochrome's state will change with it. The magnetic overlay will fade in bright conditions as other cues take over. During twilight and night, the overlay will return. The compass is context-sensitive, active when it is useful, quiet when other senses dominate. This rhythm keeps energy use balanced, preserves signal quality, and ties navigation to cycles as old as the planets spin. You reach a fallen log and trace the grain with your fingers. The wood is cold and faintly damp. You think of how often we talk about instinct as if it were an answer by itself. In truth, instinct is a set of evolved rules that invest chemistry with meaning. Look at the sky in the evening. Align the overlay with the fading glow. Store the angle. Sleep. Then go when the stars rise. Turn when the pattern on the retina says the angle is wrong. Adjust when wind pushes. Correct each hour. Repeat. The math is done by molecules, membranes, and neurons that learned this language from ancestors who survived. You stand, draw your cloak tighter against a rising breeze, and begin the walk back through the trees. The birds above are out of sight now, but their roots remain, ribbons stretched across a planet that grants no signposts you can see, and yet is full of signs if you are built to notice them. You carry with you a plain account of one such sign. Light primes a protein. A radical pair forms. Spins evolve. Yields shift with orientation. A pattern draws itself across sight. A heading is chosen. Days later, a hedge on another continent receives a familiar flutter of wings. You keep moving beneath the thinning canopy, and when you reach the forest edge, the night opens again. The valley floor lies quiet. A stream threads silver between low stones. Far away, a village folds into the dark. Your steps are slow now, not from fatigue, but from satisfaction that the picture has settled into place. You do not need to force poetry onto it. The facts are wonderful without adornment. The world works by rules that remain extraordinary even when stated plainly. You turn once more to the sky and let your eyes rest on a single star. The same physics that lets a bird bring itself home is the physics that lets that star shine. Electrons couple and decouple. Spins align and flip. Energy flows through allowed channels. The universe writes its story in such transitions, small and large, and you are within that story whether you climb a tower, follow a river, or stand still in a clearing, listening for wind beats you can no longer hear. You step beyond the clearing, the stars opening wider overhead. The forest grows quiet around you, and your mind drifts back to the stream and the birds. But now it reaches farther, out to the light of the stars themselves. You tilt your head back and let your gaze rest on a single point of light. To your eyes, it is steady, but in truth, it is a storm. A star is a nuclear furnace, fusing hydrogen into helium in reactions that release unimaginable amounts of energy. Every photon that leaves its surface began its journey deep in the core, where pressures crush atoms so tightly that protons overcome their natural repulsion and bind together. The fusion releases energy in the form of gamma rays, particles of light far more energetic than what you see. Those gamma rays scatter and collide inside the dense plasma, bouncing for thousands, sometimes millions of years before they reach the surface. By the time the light escapes into space, its energy has been stepped down, stretched into the visible colors that touch your eyes tonight. You breathe slowly, realizing that every star you see is both past and present. Light travels at a finite speed, about 300,000 kilometers per second, and many of the points above you are hundreds or thousands of light years away. What you see is not how the stars look now, but how they looked long ago when the photons began their journey. The night sky is a time machine, every dot a window into history. You are always looking into the past, and the cosmos reveals itself not as it is, but as it was. You bring your focus back to yourself, to the body that stands beneath the sky. The calcium in your bones, the oxygen in your lungs, the iron in your blood, none of these were forged on Earth. They were born in stars that lived and died long before this forest ever grew. When a star much larger than the Sun runs out of fuel, fusion halts, gravity collapses it inward, and the core rebounds in a supernova, an explosion that scatters elements across space. Hydrogen fused into helium, helium into carbon, carbon into oxygen, oxygen into silicon, and on until iron, the heaviest element stars can forge through fusion alone. The explosion spreads these elements across galaxies, seeding nebulae, where new stars and planets form. The very atoms inside you are ancient travelers, carried across eons, reassembled here, inside your skin. You are not separate from the stars. You are their continuation. You take a slow step forward, the sound of your boot softened by moss. The thought lingers, stars burn because of fusion, yet fusion is not just confined to the heavens. It is a balance of quantum forces, protons held apart by their electric charge, yet bound together by the strong nuclear force. At the temperatures and pressures in stellar cores, quantum tunneling allows protons to slip past their repulsion and bind, even when classical physics would forbid it. Without tunneling, the universe would be dark, no stars shining, no heat, no light, no life. The same strange rules that guide photons inside a leaf guide the fusion at the heart of the sun. The same quantum processes that let birds orient in flight also fuel the stars that define north and south. You look back to the flock you imagined crossing the valley. They see the stars not only as lights, but as patterns that guide them, maps that calibrate their compass. For them, the cosmos is not far away. It is a ceiling of reference points woven into their instincts. For you, it is a reminder of your origins. Every breath you take, every beat of your heart, is made possible by reactions that began billions of years ago, in stars whose ashes became the Earth. The night deepens. The Milky Way stretches like a river of fire across the sky. Billions of stars merge into a pale cloud, too many to count. You walk slowly, aware that each one has its own story, its own chemistry, its own orbiting worlds. Somewhere among them are planets where streams flow and forests grow, where creatures lift their heads and wonder at their sky. The scale humbles you. The laws that govern a single photon inside a leaf, a radical pair inside an eye, or a droplet in a stream are the same laws that govern stars and galaxies. Nature does not change its language. It only speaks at different volumes. You find a boulder and sit, letting your gaze rest on the horizon where the mountains cut against the stars. You think of the photons that touch your eyes now. They left their star long before you were born. They crossed the void without rest, untouched and unchanged, until they met your retina and became part of your perception. In a sense, they were always meant for this, carrying their message of light until they found a mind to receive it. You breathe in again, slow and steady, letting the night air fill your lungs. The oxygen you draw in was made in stars. The iron in your blood that carries it was made in stars. The carbon that structures your body was made in stars. Every second, you are in communion with the cosmos, not by poetry, but by fact. The quantum realm, the laws of physics, the processes of chemistry, these are not distant abstractions. They are here, in your breath, in your skin, in your thoughts. You rise once more and begin to walk, each step grounding you in the forest, each glance upward reminding you of the infinite. You are small, yes, but you are not insignificant. You are the universe contemplating itself, a child of stars standing beneath their light, carrying within you the same processes that govern all things. The flame of fusion burns above you. The flame of life burns within you, and the same rules guide them both. You keep walking, quiet and calm, your path stretching into the night. You keep moving along the ridge, your footsteps soft, your body quiet. The stars continue overhead, and as you walk, your thoughts shift inward, deeper into the fabric of what holds the universe together. You've traced photons inside leaves, followed electrons in a bird's eye, and touched the fusion in the heart of stars. Now, you begin to consider something stranger still, the very stage upon which all of this unfolds. Space itself. When you look upward, the stars seem scattered across a black canvas, but space is not empty. It is a field filled with fluctuations, a restless sea of energy that flickers even in the absence of matter. Quantum physics tells you that what seems like nothing is alive with virtual particles, pairs that appear and vanish in unimaginably short timescales. The vacuum is not void. It is active, frothing with potential, its fluctuations influencing how real particles behave. You stop at a bend in the trail where the forest parts to reveal the valley below. The moonlight paints the river in silver, and you think of how space itself curves around that river, around the mountains, around the planet beneath your feet. Einstein's general relativity tells you that matter and energy shape space, bending it, curving it, stretching it. Gravity is not an invisible pull from a distance. It is the geometry of the universe itself, the way space-time leans and folds in response to what exists within it. The river runs downhill not because some unseen force drags it, but because space itself has been curved by the Earth's mass, and downhill is simply the straightest possible path in that curved geometry. You take another step, and think of how quantum mechanics and relativity seem to live side by side, but never fully agree. On one scale, electrons spread in probability waves, tunneling where they should not pass, entangling across impossible distances. On another, stars collapse into black holes, warping time and space so fiercely that even light cannot escape. Between them lies a gap, a seam science has yet to mend. And yet here you are, walking in the middle of it, your own body a bridge. Your cells are crowded with proteins and molecules that fold and interact because of quantum rules. Your weight presses into the earth because of curved space. The two frameworks meet not in equations on a board, but in the rhythm of your breath, in the beating of your heart, in the quiet of your steps. The universe is not divided into two separate languages. It is one reality, layered in ways you are still learning to read. You stop once more and sit upon a stone, your cloak brushing the ground. You close your eyes and breathe deeply, the flame of stars steady in your chest. You imagine the scale of it all, the foam of quantum fluctuations of the smallest level, the sweep of galaxies bending space on the largest. And between those scales, the forest hums quietly around you, carrying both truths at once. You open your eyes and look at the sky again. It is vast, yet It is not distant. It is the same fabric that you are part of. The same fabric that lets you see, breathe, and move. You are not visitor to this realm. You are its expression. And so you rise, steady, calm, and continue your path beneath the stars. You stop at a rise where the trees thin, and you let your gaze settle on the deep sky. You decide to hold one idea steady until it becomes clear. You choose black holes. You do not want a legend. You want the mechanism, the geometry, the evidence, and where our knowledge begins to blur into open problems. You begin at the start, with collapse. A massive star spends most of its life fusing hydrogen to helium in its core. Fusion pushes outward with pressure and heat. Gravity pulls inward with weight. And for a long time, those two influences balance. As the core runs out of hydrogen, fusion steps upward through heavier fuels. Helium to carbon and oxygen, then to neon, magnesium, silicon, and at the end to iron. Iron does not yield energy when fused, so the engine stalls. Gravity tips the balance. The core collapses in a rush that lasts less than a second. Electrons and protons combine into neutrons. Neutrinos stream outward. The outer layers bounce and explode as a supernova, and what remains at the center depends on mass. If the core is below a threshold, it becomes a neutron star, supported by neutron degeneracy pressure. If the core is above that threshold, even neutrons cannot hold, and collapse continues. No known pressure stops it. A black hole forms. You picture the defining scale. For a non-rotating black hole in general relativity, the Schwarzschild radius marks the distance where the escape speed equals the speed of light. Twice the gravitational constant times mass, divided by the speed of light squared. Pack any mass inside its Schwarzschild radius, and light itself cannot escape. The event horizon is that boundary in space and time. For a black hole with the mass of the Sun, the radius is a few kilometers. For a black hole with 4 million solar masses, like the one at the center of our galaxy, the radius is about the size of Mercury's orbit. The horizon is not a material surface. It is a null surface in the geometry. A place where light that tries to climb outward simply stays fixed, then drifts inward. Outside, escape is possible. Inside, all future paths lead deeper. The phrase singularity names the place where the classical theory predicts infinite curvature. It is not a point in space that you can touch. It is a feature of the solution where the mathematics runs out. General relativity does not include quantum effects. Most physicists expect a full theory of quantum gravity to change that interior story and remove the infinity, but we do not have that finished theory yet. What we do have is a detailed description of everything outside the horizon that has passed every observational test so far. You shift from formation to structure. No rotation first. Light that orbits a non-rotating black hole in a circular path sits at the photon sphere and about 1.5 times the Schwarzschild radius. Orbits there are unstable. A small nudge sends light inward or outward. Material orbits, like gas in a disk, have a last stable circular orbit a little farther out. Inside that radius, an orbit cannot remain stable. Matter plunges inward in only a few orbits. Accretion disks heat as gas spirals in, Friction and magnetic turbulence convert gravitational energy into radiation. X-ray binaries that pair a black hole with a normal star glow in X-rays because of that heating. The growth of supermassive black holes in galaxy centers is powered by disks on much larger scales, and when accretion is high, those objects shine as quasars, brighter than entire galaxies. You add rotation next. Real black holes almost certainly spin because the stars and gas that made them carried angular momentum. A rotating black hole is described by the Kerr solution. The horizon shifts inward in places and outward in others relative to the non-rotating case, and a new region appears outside the horizon called the ergosphere. Frame dragging in the ergosphere is extreme. Space itself is pulled around with the black hole. No object can stand still there relative to distant stars. Everything is forced to rotate. Energy can be extracted from that region through processes that tap the black hole's spin. In clean theoretical form, the Penrose process shows how a particle can enter the ergosphere and exit with more energy than it had by sending a partner on a trajectory that reduces the hole's rotational energy. In astrophysical form, magnetic fields anchored in an accretion disk can couple to the rotating spacetime and launch relativistic jets. The Blandford and Znajek mechanism explains how rotational energy and magnetic fields cooperate to drive collimated beams that stretch for thousands of light years. Many radio galaxies and quasars display those jets, and they are among the most dramatic signatures of black hole activity. You consider what an infilling traveler would feel. Tidal forces stretch one direction and squeeze another. For a stellar mass black hole, those tides near the horizon can be severe. The gradient in gravity across a human body can be fatal well before the horizon if the hole is small enough. For a supermassive black hole, the horizon can be crossed without immediate destruction because the curvature gradient is gentle on that scale. In both cases, once you cross the horizon, return to the outside world is not possible according to classical general relativity. The inward direction becomes your future. You step from geometry to time. Gravity slows clocks. Put a clock near a compact mass and a clock far away, and the near clock runs slower as measured by the far one. This gravitational time dilation is not a trick. It has been measured on satellites and in laboratory towers. Near a black hole, it becomes dramatic. Light that climbs out from near the horizon is redshifted. It loses energy, its frequency drops, and to a far observer, anything that falls in seems to slow, then freeze and fade as it approaches the horizon. That is an outside view. The infilling traveler experiences the crossing as uneventful in the supermassive case, then continues inward. You move from classical to quantum effects at the horizon. Hawking radiation is a prediction that arises when you let quantum fields live on a curved spacetime with a horizon. The simple picture that many people use mentions pairs of particles near the horizon. One escapes while the partner falls in, leaving the hole lighter. The careful description uses quantum field theory and vacuum states that look different to different observers. The result is a thermal spectrum of radiation from the horizon, with a temperature that is inversely proportional to mass. Small black holes are hot. Large ones are cold. An astrophysical black hole with many solar masses is so cold that its Hawking radiation is negligible compared to the light falling on it from the universe. A supermassive black hole is colder still. Evaporation would take times far longer than the current age of the universe for any known black hole. We have not detected Hawking radiation from an astrophysical source. The effect is far too faint, but the logic that predicts it is robust within the parts of theory that we trust. Hawking radiation raises a sharp question. If a black hole evaporates completely, where does the information about the stuff that fell in go? Quantum theory says that evolution is unitary. Information is preserved in principle. The naive picture of a black hole that radiates thermally suggests information is lost, which would violate that principle. This conflict is the information paradox. Many ideas circle the problem. Black hole complementarity argues that no single observer sees a violation because exterior and interior descriptions cannot be combined in one measurement. The holographic principle says that the information content of a region can be encoded on the boundary surface, and in certain dualities like ADD, S and conformal field theory correspondences, a black hole maps to a thermal state in a lower dimensional quantum field theory where unitarity is manifest. The Page curve, which tracks entropy of the radiation as a function of time, provides a target shape for a unitary resolution, rising then falling as correlations appear. Recent work with quantum extremal surfaces and replica wormholes suggests how the correct curve can emerge from semi-classical gravity, hinting that information is not truly lost. None of this is the final word. It shows where the field is moving and how black holes remain laboratories for quantum gravity. You keep your focus on evidence. The most direct kinematic proof that a supermassive compact object sits at the center of our galaxy comes from tracking individual stars that swing around an invisible mass. Near-infrared telescopes have followed orbits very close to the central source for decades. The mass is millions of suns, and the object emits far less light than a star cluster would. No ordinary cluster can remain that tight for so long. The simplest explanation is a black hole. The Event Horizon Telescope has imaged the photon ring and surrounding emission near two galactic centers, the one in our galaxy and the one in M87. The glowing crescents are not pictures of the horizon itself. They are images of hot plasma around it, lensed by strong gravity into a ring whose size agrees with general relativity for the measured masses and distances. On smaller scales, X-ray binaries give you another line of evidence. A normal star orbits an unseen companion that is too massive and too compact to be a neutron star. The X-ray spectrum and the behavior of the disk suggests the deep potential well of a black hole. Spectral lines from iron near the disk are broadened and skewed by relativistic effects. Quasi-periodic oscillations trace motions near the last stable orbit. Continuum fitting of the heating tail and reflection spectroscopy together provide estimates of spin for some sources, and while such measurements are model-dependent, the overall agreement across methods supports the picture. You add gravitational waves to the list. LIGO and Virgo have recorded dozens of mergers of compact binaries since 2015. The waveforms match the predictions for black hole pairs spiraling together, merging, and ringing down. The ring-down frequency depends on the mass and spin of the final hole and matches the Kerr solution. Signals from neutron star mergers look different, with electromagnetic counterparts. The absence of electromagnetic counterparts in most of the heavy events matches black hole pairs. Gravitational waves let you listen to space-time respond to the most violent events, and the sound matches the theory. You widen the mass range. Stellar mass black holes form from collapse, often in the 5 to 10s of solar mass range. Some events involve heavier objects than standard stellar evolution would produce in a single step, which hints that repeated mergers inside dense clusters or disks near active galactic nuclei can build larger black holes. Intermediate mass black holes, in the hundreds to thousands of solar masses, have candidate detections in gravitational waves and in a few dense star clusters, but the census is not complete. Supermassive black holes sit in the centers of most large galaxies. They can grow by mergers and by accretion, and during quasar phases they can shine so brightly that they outshine their host. The growth of those giants connects to galaxy evolution. Feedback from jets and radiation can heat gas, shut down star formation, or trigger it in complex ways. The black hole and the galaxy co-evolve. You touch the cleanest theory statements. In general relativity, stationary black holes in vacuum are described by a small set of parameters: mass, spin, and if present, electric charge. The no-hair theorems say there are no other independent multipoles for the exterior field beyond those built from mass and spin for astrophysical black holes, because large-scale net charge would be neutralized quickly by surrounding plasma. Tests look for deviations in the multipole structure of the gravitational field through precession and ring-down modes. So far, the data fit care. Precision will improve as detectors grow more sensitive and as pulsar timing arrays build catalogs. You contrast horizon concepts. The event horizon depends on the entire future history of space-time. It is a global surface. Apparent horizons and trapped surfaces can be defined locally. In dynamical situations like mergers, numerical relativity tracks those local horizons and the geometries that evolve around them. In that picture, a black hole is not an abstract edge, but a region that swallows light cones so that all world lines tilt inward. The mathematics is heavy, yet the intuition is simple. Outside, there is a way out. Inside, there is not. You return to accretion and light. Gas falling into a potential well converts a large fraction of its rest mass energy into radiation. Accretion can be more efficient than nuclear fusion at turning mass into light. Thin disks radiate efficiently. Thick and advection-dominated flows trap more heat and shine less brightly. Magnetic fields grow through turbulence, reconnect, and launch winds. The coupling between magnetic fields and rotation is what lets disks transport angular momentum outward so that mass can move inward. Observations of spectral states in X-ray binaries, transitions between soft and hard states, and the timing behavior of flares all reflect those flow regimes. You let one more practical point settle. Falling in is easy. Getting out is impossible once you cross the horizon, but long before that boundary, there are signatures that let astronomers weigh and map the region. Stellar orbits give dynamical mass. Disk spectra give spin estimates. Iron lines give strong field distortions. Jets give magnetic and rotational coupling. Gravitational waves give clean tests of strong gravity. The set is coherent. Independent channels point to the same object class. You close with two edges of knowledge. First, the interior. General relativity predicts a singularity. Quantum field theory on curved spacetime predicts Hawking radiation outside. The full quantum spacetime story remains incomplete. Second, the information problem. The trend of recent work supports preservation of information, but the detailed mechanism as realized in our universe, not in an idealized dual theory, is still being clarified. Black holes are not only dark endpoints, they are tools for asking the most precise questions about how space-time and quantum theory fit together. You take a breath and feel grounded. You have the outline. Formation by collapse. Geometry that shapes light and time. rotation and frame dragging, disks and jets, evidence across the spectrum, and in gravitational waves, quantum effects that illuminate paradox, point toward deeper theory. A black hole is not a myth hiding behind jargon. It is a physical solution that the universe builds often, a place where the rules you have learned elsewhere reach their strongest expression. You stand on the ridge, the forest at your back, and the sky ahead, and you let the picture hold still long enough that it becomes part of how you see the world. You linger at the ridge, the forest silent around you, the stars infinite overhead. The story of black holes settles in your mind like a weight, both steady and vast. You have walked through their formation, their horizons, their geometry, their radiation, their paradoxes, their evidence. You have seen how they shape galaxies, how they bend light, how they thrum through space-time with waves you can now hear. You realize that black holes are not monsters waiting in darkness. They are the universe's most honest expressions of its own rules. Gravity pushed to its extreme. Quantum physics stretched to its edge. Light, time, and matter braided into one inescapable pattern. To look at a black hole is to see the boundary of knowledge itself, and beyond that horizon, questions still wait. You breathe deeply, filling your lungs with air heavy with pine and soil. The forest, the stars, your heartbeat, all of it, is written in the same physics that carves horizons and collapses stars. You are not separate from it. You are not a spectator. You are an instance of those same rules, alive and aware, able to understand just enough to marvel. You step down from the ridge and into the trees once more. The night folds around you, not heavy, but calm. The flame in your chest is steady, not a burden, but a reminder. You are stardust that learned to walk. You are water that learned to see. You are atoms forged in fire that now stand beneath the sky to contemplate it. And as you walk deeper into the forest, you know that the story does not end with the tower, with the forest, or with the black hole. It continues, always, written in the laws that shape everything from the smallest flicker of a photon to the largest curve of space-time. The path is open, and you walk it quietly, flame steady, stars watching, universe within you and around you, forever unfolding.